Okay, well, thank you for inviting me to give this talk. Um, so this is a session about future technology. I'm not going to talk very much about that. What I'm going to talk about is how, in particular, how technology over the last 20 years has made a lot of advances and opened a lot of questions. So I'm going to throw the questions out and maybe make a few suggestions of how technology can help, but mostly here's some things that I think uh, we need to address. And I'm an isotope geochemist, so I look at this from that perspective. Um, so, first of all, the Earth's formation and composition, as I'll show you, we've made a lot of progress, but that progress has raised other questions. Continental crust formation through time. Um, how much was created uh, and how much destroyed? Why is crust formation or its survival punctuated in time? Why is Archean crust different than post-Archean crust? Why was there another change in the Neoproterozoic? When did modern plate tectonics begin? Um, why did the oxygen in the Earth's atmosphere change dramatically twice? Again, in the Neoproterozoic and in the Paleoproterozoic. Hmm. Is there a connection between those things? And then going into the deep mantle. These LLSVPs at the base of the mantle. What are they? What are they made of? How have they evolved through time? Are they persistent? And then the real question is, does the deep mantle ultimately control evolution at the surface of the Earth or vice versa? Does the surface of the Earth control evolution of the deep mantle? I think is a big question. Okay, starting with solar system formation. Again, I'm an isotope geochemist. So um, these are isotope ratios in, here is achondritic meteorites, and these are chondritic meteorites. And you can see a big division between the two. These isotope ratios reflect differences in nucleosynthesis, the way the elements were created, whether they're created in the S process in red giants or the R and P process in supernova and kilonova. Okay, there's a big difference. So the solar system isn't homogeneous. And it turns out, what we think is, this is the outer solar system, this is the inner solar system. And a widely accepted model now is the grand tack model, where the formation of Jupiter and Saturn, first of all, formed initially a boundary between the outer and the inner. And then the trees migrate inward, sort of mix everything. Um, and the result is that we get I guess I should do that. Yeah, if I'm going to move away. The result is we get outer solar system material in the inner solar system, uh, such as the asteroid Ryugu, which is a carbonaceous chondrite, but that formed in the outer solar system. So probably these carbonaceous chondrites are responsible to the fact that the Earth has water, for example. Okay, but there's other problems here, and that is that we have all these different kinds of meteorites, all of them different, and there's no way you can mix them together and make the Earth. The Earth, in fact, is richer in S process material than all the other things we have. So S process produced in red giants. So the, there's a missing ingredient here. The question is, wait a minute, it's supposed to be, this is the question. Is there a possible missing solar system, inner solar system ingredient? So a suggestion for the next Hayabusa mission might be to look for something that looks more like mercury than carbonaceous chondrites. We're missing something. Okay, and even with that, even taking account of these differences in nucleosynthesis, it turns out that the Earth has excess neodymium-142, which can only mean that it has a higher samarium neodymium ratio uh, than um, uh, than than chondrites. Okay, so, and that has to be chemical. So there's some sort of chemical fractionation going on. One of the ideas is, that's been around for quite a while, is this collisional erosion. And we know the last stages of giant planet formation involve large collisions. The idea is every time you have a collision, you form a new crust. It's basaltic, it's enriched in incompatible elements. The next collision to come along blasts that stuff off. Eventually, you deplete the Earth in incompatible elements, and that includes the heat-producing elements, like uranium, thorium, and lead, uranium, thorium, and potassium. And so one way to constrain this, which is, the Camland geoneutrino detector is making a lot of progress, is to try to measure the neutrinos from uranium and thorium. And this is Bill McDonough's slide. You can see that the results so far still leave a lot of open question. Okay, so we cannot yet tie down very well uranium and thorium, but in principle, in the future, with additional observations, we might be, particularly ocean bottom geoneutrino detector could help us resolve this. Okay, on to crustal evolution. The ability to in situ determine lead ages of zircons have shown that we have zircons or parts of them as old as 4.4 billion years. Okay, and now we've found these on every continent basically except Antarctica. There was a lot of Hadean crust. What happened to it? Further progress comes from the ability to measure hafnium isotope ratios as well as lead isotope ages in situ. Let me explain this diagram. This is basically hafnium isotope ratios. Something purely from the mantle would evolve with time like this. If you have old crust and you just reprocess it through metamorphism, it evolves like this. If you mix new mantle-derived material with old mantle-derived material, it mixes like that. So if we look at the data, what we see is we have both. We have new additions to crust. Here we are. Here's the end of the Hadean. We have new additions to crust, but also there's a lot of the data plotting along here, which looks like Hadean crust that's simply been reprocessed. The point is, there actually was a lot of Hadean crust, but it's all gone. By definition, we have no Hadean crust. Okay, so what happened to it? And the fact that it's lying along here suggests a lot of it was simply recycled into new crust. But how much was there and how much remains is unclear with this crust. Now, the other thing about crustal genesis, these are the ages of zircons. These are igneous ones, these are detrital ones. These ages are very much punctuated in time, appear to correspond to supercontinent cycles. So why is that? Okay, and one of the debates is, does this reflect new production of continental crust or simply whether it's preserved in origins? I'm not going to tell you the answer. That's the question. The other thing is, if we then look at hafnium isotope ratios in those zircons, we can see that in fact, this looks like we have increasing crustal production through time, but this is the cumulative crust. More than half the crust would have been created by the end of the Archean. Okay. Now, speaking of that, what happens to the crust? This is a slide from Bob Stern of two different assessments of what the present fluxes of continental crust into the mantle are. And you can compare, this is the total crustal additions, total crustal losses, total crustal additions, total crustal losses. It looks like, based on this, that the volume of the crust is more or less steady state. We're destroying it at the same rate it's being produced. But has that been true throughout time? Good question. We don't know. Okay. Now, the other thing about crustal evolution is Archean crust is somehow fundamentally different. This is a slide from Kent Condi showing the distribution of TTG, or tonalite trondhjemite granodiorite suites, which dominate the Archean and then more or less disappear at the end of the Archean. Something's fundamentally different. And this is work of Brennan Kelleher, who was actually an undergraduate student of mine and published this paper 2 years after he graduated from Cornell with a bachelor's degree. Remarkable, I thought. Um, but so this is MGO through time. This is the Archean, post-Archean, the lanthanum-samarium ratio. Basically, what you see is a dramatic, and these are crustal rocks, dramatic transition through the Archean and the early Proterozoic in the composition of continental crust. So, a number of people have talked about tectonic transitions in the Neoproterozoic as well. Here's the number of orogenic collisions, again from Ken Condi. You see the spikes in the Neoproterozoic and the Paleoproterozoic. Brown and others argue for a transition here. We only see high pressure, low temperature metamorphism after the Neoproterozoic. We see more metamorphic belts after the Proterozoic. So, a number of people arguing for transitions in the Neoproterozoic and the Paleoproterozoic. Very interesting. When did plate tectonics begin? I don't know, and neither does anybody else. I think it's the point here. This is a slide from Palin and others showing where people think plate tectonics might have begun. And the answers are all over the place, but they're mostly in the Archean or the Neoproterozoic. Nobody really thinks it began in the main part of the Proterozoic or in the Phanerozoic. So that's a big debate. I don't know what the answer is, but it's very interesting again that the people think Paleoproterozoic, Neoproterozoic. Okay, well, at the surface of the Earth, meanwhile, there's another big transition in the Paleoproterozoic. Okay, this is mass independently fractionated sulfur isotopes through time. You see the sudden transition. These mass independently fractionated isotope ratios are a result of UV photolysis of sulfur dioxide in the atmosphere. And it indicates that UV radiation could penetrate through the whole atmosphere, unlike now, because it's absorbed now by oxygen and ozone in the stratosphere. So this is an indication of oxygenation in the atmosphere rather suddenly at the end of the Archean. This is a slide from Lyons and all, and they're showing low oxygen all the way through the Archean. This relatively sudden jump stabilizes through what's called the boring billion of the Proterozoic, and another jump in the Neoproterozoic. Now, is that a coincidence? Okay, now, so why did it increase why the sudden increase? It's not because photosynthesis was invented there. Here's some more isotope evidence. This is molybdenum isotope ratios in sediments. You see, here's sort of this is the modern seawater level in a Earth without oxygen in the atmosphere. Molybdenum should be close to the crustal or mantle value, as it is in the early Archean. Then in the mid-Archean, it starts to rise up like this. So the molybdenum isotope variation reflects redox fractionations, no oxygen, no redox reactions. We're already having redox reactions in the late Archean, meaning photosynthesis began sometime before that. And then you can see another transition here, and this carbon isotopes indicating disturbances in the carbon cycle. Okay? Another transition at the end of the Phanerozoic, and this coincides, of course, with that rise in oxygen, also with the first appearance of animals. So that's very interesting. It's two very interesting times. All right, let's go into the deep Earth. One of the remarkable discoveries of the last 20 years has been the recognition of these large, low S-wave velocity provinces. Okay, so it looks like they're hot, but they also suggest compositional boundaries because the boundaries are too sharp to be purely thermal. They're big, occupying maybe 5% of the mantle mass. That's 10 times the volume of the continents. They rise as far as 1,000 kilometers off the core mantle boundary. There's approximately antipodal. What are they? Are they primordial material from magma oceans, subducted oceanic crust, or something else? And it turns out mantle plumes are connected to them. This is the work of French and others. Seismic tomography, for example, Comoros and St. Helena, Hawaii up there, we can connect mantle plumes seismically down to these LLSVPs. It turns out, as Clive O'Neill pointed out yesterday, most of the plumes actually come from the edges of these LLSVPs. Okay. Now, one thing we know about plumes is they contain recycled material from the surface of the Earth. This is Samoan data. Oxygen versus, this is oxygen versus strontium isotope ratios in olivines. And we see this correlation between the two. Oxygen isotopes are only going to, fractionation is only going to occur near the surface of the Earth because it's strongly temperature dependent. This is superficial material. We see the same thing in sulfur isotope ratios. Again, the only way to fractionate these stable isotopes is at low temperature near the surface of the Earth. This is clear evidence that we have recycled material in the deep Earth. Okay, now, but there's also primordial material that mantle plumes are bringing to the surface. Okay, so I mentioned the samarium, the extinct radionuclide. Here's another one. Hafnium-182 decays to tungsten-182. And this mu-182 tungsten is a measure of the difference between tungsten in these oceanic island basalts and a standard, typical Earth values. We see this clear correlation with helium isotope ratios. High 3-4 means something more primordial, less degassed. So there's plumes also contain stuff that's less degassed, has this anomalous tungsten because of the short half-life of hafnium that must have been created in the first few tens of millions of years of solar system history. And this is plotted versus neodymium isotopes. Okay, so plumes have both primordial component and a recycled component. Geodynamicists, this is one of my favorites from Lee and McNamara. Their idea is that somehow the yellow is subducted oceanic crust, the green is more primitive. These are the LLSVPs. This material, first of all, the LLSVPs work as waveguides to start the plumes, and they can eventually pull in both recycled and primordial material. But then there's the question of how the LLSVPs were formed in the first place, and whether plate tectonics controls their location and their creation, or whether they control plate tectonics and continent formation. So this idea from Li and Zhong, the idea is you get mantle plumes that create a supercontinent. Eventually there's subduction around the supercontinent, forces hot mantle towards the center, produces more mantle plumes that break up the supercontinent. So their idea is LLSVPs are driven by supercontinent cycles. On the other hand, Jablonski and Dvorak have argued based on the position of large igneous provinces through time that the LLSVPs have always been where they are. And that in turn, they control plate tectonics. So the question is, what's the answer to that? And I'm not sure. But so here's the big question. Are tectonic transitions of deep mantle and atmospheric O2 linked? Tectonism and volcanism has two effects. One is volcanism, tectonism deliver nutrients to the ocean, without which there's no life. And so some of the this is a key thing in photosynthesis. If you don't have phosphorus in the ocean, you can't evolve for photosynthesis and can't get an oxidizing atmosphere. So maybe tectonics is what drives this. And some people think that lack of tectonics at the end of the Neoproterozoic basically shut down life to a fair amount, and the oxygen couldn't rise anymore. Um, Other ideas, on the other hand, volcanism supplies reducing components. It's going to deprive the atmosphere of oxygen. And Connie's argued for a lull in the the Paleoproterozoic that allowed oxygen to rise. Another idea, Neil and Auerbach, suggests an oxidized layer deep in the Earth rises in the Neoproterozoic, bringing rises carried by mantle plumes, rises to the surface at that time. Okay, so here's my summary. The deep Earth and the shallow Earth are connected. The question is how, okay? So the Earth's evolved in a very non-linear manner, both in terms of the surface, in terms of tectonics. There have been significant transitions, even though we don't know the details. The deep mantle contains the largest structures on the Earth, these LLSVPs, that generate mantle plumes. Material from the Earth's surface has been subducted all the way to the bottom of the mantle and is returned to the Earth, returned to the surface by these mantle plumes. And perhaps subduction actually controls and creates these LLSVPs, perhaps not. But these LLSVPs also contain material which has more or less been isolated for more or less the entire history of the Earth. And so mantle plumes influence plate tectonics, break up continents, and provide rich nutrients for the Earth's biosphere. Again, shallow and deep Earth are intimately connected, but the details of those connections are poorly understood. So a lot of progress in the last 2 decades, which has raised a lot of new questions, and that's where we should focus technology on answering those questions. Thank you. Speaking of that, I'll answer your questions.